You know how to find the area under a curve. Now let's go one dimension higher. Volume under a surface. Quick recall. A single integral sums up thin rectangles to get area. Now imagine adding a second dimension. Here's f of x. Y equals 4 minus x squared minus y squared. A dome shape. Chop the base into a grid of tiny squares. At each square, build a column up to the surface. The volume is roughly the sum of all column volumes. Height times base area. Make the grid finer. 9 columns. 49. 225. In the limit. Infinitely many infinitely thin columns. The sum becomes a double integral. Exact volume. Here's how to compute it. Fix x and look at the cross-section. For each x, integrate over y to get the area A of x. Watch the slice change shape as x increases. Near 0, the slice is tall. As x grows, it shrinks. Now stack all those cross-sections together. Each slice has area A of x. Integrate A of x over x. And you get the total volume. That's the iterated integral. The double integral in action. Fubini's theorem says you can swap the order of integration. Slice vertically. Fix x. Integrate y first or slice horizontally. Fix y. Integrate x first, either way. Same volume. This flexibility is incredibly useful. For circular regions, polar coordinates are natural. The grid becomes concentric rings and radial slices. Each tiny cell is a wedge. Its area is r times d theta. That extra r factor is crucial. It accounts for cells getting bigger farther from the origin. Double integrals. Sum columns to get volume. Compute as iterated integrals. Slice one direction, then the other. Fubini says the order doesn't matter. For circular regions, switch to polar and don't forget the extra r. Thanks for watching. Subscribe to Zari Gatongi for more math explained visually. And visit 8gramswifi.org/math.